When you think of how cities would look like in the future, what do you see? Cities have been around for tens, hundreds, even thousands of years. Look how they look like today. In the past years, there has been a tremendous advancement in the civil engineering and construction industry. And all of that was achievable through hard work and technology. In the past decade, engineers have greatly improved on obtaining denser amounts of information with efficient devices and powerful processes. The need for transparency in plans, information, and documentation are all possible with a particular focus: laser scanning technology. I'm not saying we have lightsabers and holograms yet, but the devices and systems that can be an important tool in building the cities of the future. Although it's a developing system with years of improvement ahead, it is effectively emerging as a prominent component in the civil engineering industry, as it provides faster and more accurate data in areas such as structures, design, and imaging. The general idea of how the devices and system operates is by sending out a pulse of a laser beam of light. The system measures the beam's time of flight, recording the time it takes for the light to hit a surface and make its return. The scanner can calculate the beam's horizontal and vertical angles, giving an accurate X, Y, and Z coordinate. The point is then recorded into a 3D visualization program. One of the driving limitations it holds is that the laser scanning is a line of sight technology, meaning it cannot see through walls, slabs, or ceilings. The placement of the scanning device is important, and the transportation of the apparatus can be tedious. This issue has been analyzed by many, leading to attempts to develop a solution. The development of an innovative mobile laser scanning method, MLS, for a 3D indoor map is an application introduced a couple of years ago by an architectural department of a university in China. The generally accepted and used procedure for this type of mapping is usually performed using a static terrestrial laser scanning, TLS, which is expensive and tedious to work with. Compared with the conventional TLS, the developed method proposes a new idea with advantages of low cost, high mobility, and time saving on the implementation of a 3D indoor map. Think about it. Imagine carrying around a scanner like a cell phone. Scan and record a virtual model of a room you're in right now. Pretty cool, right? Their device is comprised of simpler mechanisms which together can capture an experimental indoor environment through developed programming algorithms. Even though the accuracy of the MLS is lower than that of a stationary system due to the physical movement, it has been significantly improved with advances in this technology. The analysis of the results in this study indicate that the potential implementation of this low-cost indoor MLS method is possible. However, due to some technical limitations in the experiment, this method should further be improved in performance and reliability. It is still, however, a strong potential for the future of the architecture, engineering, and construction industry. As scanning processes become more sophisticated every year, investigations on fusing laser scanners with other devices have become more popular. Cameras and photography, for example, are essential in photogrammetry software and record. Photography alone can be much cheaper than a TLS instrument and provides not only 3D documentation of the object measured, but also a high-textured resolution image, which can help to analyze the state of a timber truss member, as observed in a particular study a couple of years ago. The main issues for the use of photogrammetry for measurement of timber truss structures are the bad illumination conditions and the complexity of the structures. In response, more images were taken, which involved more time-consuming processing. The use of a total station for ground control measurement was also necessary. In contrast, laser scanning can operate regardless of lighting levels, and it can produce a great number of points from defining the geometry of the structure, and implementing this device could fill in the blanks where photogrammetry system failed. In a more recent study from Poland, the devices that were combined involved the laser scanner and a surveying total station. The Leica TDR 6000 laser scanner helped define horizontal and vertical displacements of a control network established in the testing facility. The far-focus M scanner, in response, configured to the data it was being shared. The basic idea is that the functions of both apparatuses are joined in order to provide a structure as a whole in a uniform coordinate system. Having a detailed model can then be analyzed for determining deformations of engineering structures. Since the dynamics of the structure changes are relatively small compared to the parameters, the measurements taken must be highly accurate. Not only did the data meet the limited uncertainty, but the technique also proved to be less labor-intensive and less time-consuming. Just like any other technological advancement, it takes time and development for it to be perfected for customary use. Its applications in structures, design, and imaging have proven effective, and is expected to improve over the years. With a stable system, the preservation of historic buildings, remodeled structures, and new construction would be accessible from any internet access. Upon completion of a construction project, the client has permanent documentation of the actual conditions as it was built. This can then be referred to in the future when determining when a new mechanical system could be added. Having a safer, more efficient, and proactive approach towards a new project will improve its development and avoid costly changes in the future. With technology like this, we will all see the city of tomorrow, sooner than you think. Thank you.